Okay, so this video is going to be a bit longer than our usual, so if you need to grab a cup of coffee, go grab one, because we are diving into fuel injection systems, its hows and whys. Before fuel injections, we had a system comprising of a carburetor, a mechanical fuel pump, a distributor, and usually one ignition coil. These engines generally produced less power, more emissions, and had to be tuned regularly. Air filters had to be cleaned or replaced more frequently than engines with fuel injection. In a fuel injection system, the injectors are only opened a few milliseconds at a time, thereby limiting the amount of fuel into the combustion chamber. Carburetors, on the other hand, have jets that continuously feed fuel into the intake manifold through a venturi and then into the combustion chamber. It doesn't allow a constant 14.7 to 1 air-fuel ratio. Introduction to fuel injection systems. This is ultimately what the ECU was made for. It controls the ignition system, the fuel injection system, and various other components so that there is increased engine efficiency and decreased exhaust emissions. Construction. It is basically a computer specifically designed to read data coming from the engine sensors, making decisions and executing commands. Operation of the ECU sensor signals. These signals can be digital or analog. The digital signals can be either an on or off value, while the analog signals have an infinite number of values with a certain range but need to be converted to digital before reaching the ECU's processor, and it is still done within the ECU. Output signals. There are many devices, but we are going to be focusing on two: the fuel injectors and the ignition coil. The fuel injectors are electromagnetic valves that spray fuel into the inlet manifold and are controlled by the ECU. The injection coil creates a spark by building and collapsing a magnetic field and is controlled either by the ECU or the ignition module. Power supplies. The sensors and output devices in the ECU use two different 12-volt power supplies in two different circuits. The one is continuous and comes directly from the battery, and the other is switched on and off with the ignition key. Processing data. The microcomputer is made up of the input-output unit, the CPU, the EEPROM or electronically programmable read-only memory, and data lines. Signals come from the sensors and are sent to the CPU, where it is processed and then sent out. The signal then goes to a microprocessor, where it is compared to pre-programmed tables which are stored in the ROM, also called the read-only memory. Newer vehicles have either electronically programmable read-only memories, EEPROM with one E, or electronically erasable program read-only memories, E2PROMs with two E's. The CPU will search the maps for data that matches the readings that come in with the sensors, and then execute commands based on what it finds. If there is a faulty sensor and the data sent is continually corrupted, a DCT or diagnostic trouble code is created and stored in the EEPROM. It is designed so that even if the battery is disconnected, the code will remain stored. The code can only be cleared with a diagnostic tester. If there is too much sensor data failure or the ECU is damaged, the engine will run in limited operation strategy or loss mode. The ignition timing will be set to a fixed value, and the fuel mixture will stay rich so that the vehicle can be driven in for a service. Other sensors will measure air to fuel ratio and the engine's load, speed and temperature. Crankshaft position sensor or CKP sensor. This is a very important sensor and is therefore called a primary sensor. If there is no signal from this sensor, the engine won't start at all. It is an inductive pulse generator that scans a toothed ring on the flywheel and is used by the ECU as a reference point for the crankshaft position. The toothed ring will either have one or two teeth missing depending on the model, and is located 9 degrees before TDC, or top dead center, of cylinder 1 on 4-cylinder engines. The gap between the CKP sensor and the flywheel is present when it is mounted on the cylinder block and is used to monitor the crankshaft position and engine speed. The camshaft position sensor. This is located on the valve cover and is used to identify cylinder 1. Knock sensor. If the engine has one of these, it will be between cylinder 2 and 3. It has a piezo element and is designed to pick up mechanical vibrations. It is there to allow precise spark timing, therefore reducing fuel consumption. If there is a knock control system, the ignition timing will increase 1/4 of a degree at a time, and this will happen thousands of times a second. If a ping or knock is sensed by the ECU, it will delay the timing between 2 to 7 degrees depending on the management system and engine load. From there, the ECU will increase timing again. This will ensure that the timing will always be ideal for that specific operation of the engine. Heated oxygen sensor. This is a signal generating sensor that works like a battery and measures the amount of oxygen in the exhaust. It has an operating temperature of 300 degrees and is therefore equipped with a heating element that is activated when the ignition is turned on. The only power supply it needs is for the heating element and is grounded via the connector to the ECU. It detects oxygen ions, and when this happens, it sends a voltage of 0.1 to 0.9 volts at 0.2 milliamps, depending on the residual oxygen content of the exhaust emissions. A rich mixture means less oxygen and higher sensor voltage, while a lean mixture, more oxygen and lower sensor voltage. The lambda control subsystem consists of the 3-way catalyst converter, the oxygen sensor, and the ECU. Because the engine conditions change constantly, the amount of oxygen in the exhaust gas also changes constantly. This subsystem changes the mixture from rich to lean, but always keeps it within a very narrow range. Then there is a second heat sensor located behind the CAT so that the ECU can compare the two sensors, thereby improving diagnostic characteristics and reducing exhaust emissions. The throttle position sensor. This is a potentiometer and is mounted on the bracket of the throttle housing and measures the amount of throttle opening. The wider the opening, the higher the voltage. Idle will be between 0.4 and 1.4 volts, while wide open will be between 4.4 to 4.8 volts. As the throttle plate opens, a sliding contact moves along a resistor track, causing the resistance to change from the reference voltage of 4.8 volts to change to an output voltage that corresponds with the throttle position. If the voltage goes above 4.8 volts or below 0.4 volts, the sensor should be tested. When reading the output voltage, the ECU will recognize 3 throttle positions: closed throttle, where the engine is either idling or on overrun; partially open throttle, which is normal operation; and wide open throttle, which is anything from 70% open and more. Similarly, the operating range of the throttle position sensor has 3 categories: idle or closed throttle, which is needed for idle speed control and overrun fuel shutoff; partial load or partially open throttle. This is needed to regulate the air-fuel mixture and keeping it at 4.7 to 1 and for emission control. Full load or wide open throttle, which is needed when there is an open loop on the system. The voltages in these 3 categories, or sometimes called transitions, can vary depending on the engine. The manifold absolute pressure or MAP sensor. This measures the amount of pressure in the inlet manifold. It is either connected by a vacuum hose to the air inlet, mounted to the body on the rear side of the engine compartment, or to the intake manifold. It allows the ECU to monitor the engine load. As the engine load increases, the vacuum force on the inlet manifold decreases, and the inverse is also true. The ECU will calculate atmospheric pressure when the engine first starts and when the throttle is wide open. If there is a problem with the map sensor, the ECU will default to settings at sea level. It receives a reference voltage of 5 volts from the ECU and converts it to an on-off frequency. As the throttle is opened, the map sensor will create a lower frequency which is sent back to the ECU and then is compared to the pre-programmed maps. And then when the throttle is closed, the map sensor will be at between 100 to 108 Hz. Mass airflow sensor. There are quite a few variations of MAF sensors, including hot wire, hot film, vane meter, Kalman vortex, and cold wire, but they all do a similar job. They measure the amount of air drawn into the engine. The hot wire and hot film are cooled as the air is measured, and the ECU will supply it with the necessary voltage to keep it at a certain temperature. And this amount of voltage is compared to the mapping in the ECU. Engine coolant temperature sensor. This is a temperature dependent sensor with a negative temperature coefficient and is located in the engine's coolant circuit. Like the name suggests, it is there to measure the temperature of the coolant. The voltage sent from the ECT to the ECU is assigned a temperature value, and when the signal is received, the ECU can boost the map where needed if the engine is cold. It is used to calculate idle speed, ignition point, and fuel quantity. Intake air temperature sensor. This measures the air entering the combustion chamber and is located in the air chamber before the throttle plate. It works similarly to the ECT in that it is temperature dependent and has a negative temperature coefficient, but the temperature changes are faster. The temperature is needed to determine the fuel quantity. Vehicle speed sensor. These work on what is called a Hall principle, and the resulting frequency is sent to the ECU. Higher speed means higher frequency. This measurement is needed by the ECU for the idle air control, fuel enrichment when accelerating, the overrun fuel shutoff, supply of the trip computer, and the speed limiter. Engine load indicators. These help the ECU monitor various devices that are driven by the engine. The ECU in turn makes changes to the air-fuel mixture so that the engine does not stall. Switches. The air conditioning switch, power steering pressure switch, and brake switch all send signals to the ECU and can be anything from 0 to 12 volts. Alternators. These also place a load on the engine and is monitored by the ECU by a series of sensors. General. After comparing all the aforementioned signals to the maps in the EEPROM, it will send signals via the outputs so that the engine performance and efficiency is properly managed. Output devices. These are all controlled by the ECU to operate items such as power and fuel pump relays, injectors, coils, the EGR system, and the air conditioning clutch. Electronic ignition system. Back in the day, this system used to be a mechanical system, but because these days it is all electronic, there is no wear. The function of the contact breaker and the Hall sensor have been replaced by the crankshaft position sensor that we spoke about earlier. This is also controlled by the ECU. It sends a high voltage to the ignition coils. The EI system controls the optimum dwell angle, the primary circuits, and the ignition timing during the limited operation strategy, which we will go through later. Electronic ignition coil. In this system, current is sent to the spark plugs via the ignition coil. It travels from the ignition coil's negative terminal, through the ignition cable, across the first spark plug gap, through the engine block, across the second spark plug gap, through the ignition cable, back to the positive terminal on the coil. The signal is only sent to 2 spark plugs because the cylinder works in pairs. One cylinder will be on the combustion stroke and the other will be on the exhaust stroke. The number of ignition circuits depends on the number of cylinders. There are 2 circuits for a 4-cylinder, 1 and 4, and 2 and 3. Then there are 3 circuits for a 6-cylinder, 1 and 5, 4 and 3, and 2 and 6. Coil on plug system. This is the system where the ignition coil is located on the top part of the spark plug and will either have 2 or 3 pin connectors. The 2-pin system has the igniter in the ECU and the 3-pin has the igniter in the coil. Limited operation strategy. This is initiated when the EI cannot identify 5 consecutive Spark Advanced Word or SAW signals or SAW signals and will compensate for the signals missing. If it cannot identify values matching what is stored in the EI, the primary circuit will function using the last stored ignition point data. This happens when the PIP signal switches the positive and negative peaks. When in loss mode, the ignition formed is fixed at 1 degree before TDC. If the EI detects 3 consecutive correct signals, normal operation will resume. Fuel systems. There are 2 primary types of fuel injection systems: multi-point injection and throttle body injection systems, commonly known as PMI and TBI. Multi-point systems have 1 injection per cylinder, and the throttle body system have a single centrally mounted injector. MPI uses 3 different types of operations: simultaneous injection, group injection, and sequential injection. Air coming into the cylinders passes through a plenum and is controlled by the throttle plate. The amount of air coming into the cylinders is monitored by various sensors. When the air flows past the inlet value, fuel is injected and a mixture is formed in the intense heat. The mixture ratio and timing for when to inject the fuel is monitored by the ECU and is constantly being monitored. TBI works on a similar principle to PMI, but looks a lot like a carburetor. Fuel delivery. From the tank, fuel is pumped into an electric tank pump through a filter to a fuel rail, then to the injectors. Here again there are 2 systems that are used: the return type system and the return list system. The return system has a fuel regulator close to the injectors and pipe leading back to the tank. A return list system has a pressure regulator in the tank itself. Mixture formation. This is formed in the inlet manifold and the engine cylinder. The injectors can either be energized in groups, like we spoke about earlier, or individually in the case of a sequential fuel injector. Idle speed control. This is again controlled by the ECU and is key in maintaining the idle speed in all conditions. When the idle throttle position from the throttle position sensor is received, the CKP sensor is monitored and the data coming from it is compared with the data stored. If the idle speed is too low, the ignition timing is advanced and the idle air control is activated. When normal idle speed is restored, ignition timing goes back to the speed set in the ECU. Idle speed adjustment. This happens whenever the air conditioning is switched on, the power steering is activated, heating for the windscreen and rear window are switched on. The air-fuel mixture is adjusted by actuating the idle air control value near to the ECU. Air conditioning cycling clutch switch. The air conditioning is receiving 12 volts power to work, and this in turn boosts the set idle speed. The actuator is turned on, but only if the de-ice or air conditioning switches have not responded. Power steering pressure switch. In a hydraulic power steering system, when turning the steering wheel, the motion triggers the power steering pressure switch, which triggers the system's oil pressure. This also activates an idle speed boost. There will be a similar system for electrical power steering. It is connected to the ECU and to ground. Heated windscreen and rear window. This is another system that when it is turned on, the ECU boosts the idle speed, which compensates for the power draw. Idle air control valve. In most systems this is present, and you don't have to touch it. In the MPI system, it is used by the ECU and is located in a throttle bypass. As the mixture is increased, the idle speed is adjusted. The valve is controlled by the ECU and is switched by ground pulses, which are calculated from the sensors and the switching signals. Please like and subscribe. Keep on the lookout for more upcoming videos.